Now let's discuss the representations of a graph on a computer. Once we define a graph, we want to store this graph on a computer, write algorithms on these graphs, and solve problems using these algorithms. The question is, how do you store a graph on a machine? There are three classic ways to store graphs on a computer: edge list, adjacency list, and matrix. So what is an edge list? So edge list stores the vertices as a sequence. It can be array or it can be a linked list, and stores edges as a sequence with pointer to vertices. For example, here is an edge list data structure. When you have edges is stored as a linked list, and vertices are also stored as a linked list. And then edges have two extra pointers, which points to their corresponding vertices. The edges may have labels, so we need to have one more pointer which points at their labels. And vertices may have names, so we need to have one pointer to point at their names. So what is the cost of computing adjacent V? Given the vertices V, you want to find out which are their neighbors. This is quite an expensive task. You need to traverse all the edges to find that where each node occurs. Let's look at the second way of storing a graph on a machine. You have, this is called adjacency list. In the adjacency list, what you have is that first you have an array of nodes which list all the vertices A, B, C, D, E. Then each of these nodes pointing at a linked list which describes the set of edges that are connected to that node. You can notice that if it is undirected graph, so you need to have A is adjacent to B, then the B must be adjacent to A. So that an edge may occur two times in this data structure. So the space complexity of this data structure is that first you need to have this backbone list of vertices, and then each node appears as many times as the total degree of these nodes, which is twice as the number of edges in the case of undirected graph. So therefore, total storage cost is V plus E. Let's look at a third kind of data structure that can store a graph A, B, C, D, E, and it can be simply stored as a two-dimensional matrix. Here's an example. Here you have a graph with the 5 nodes. Then you create a matrix of 5 by 5. And since this is undirected graph, you don't need to worry too much that A is connected to B connected to A. So you can see that whenever two nodes are connected, that bit is set to 1. The space complexity of storing such a data structure is V square. So what is the cost of adding a node? So when you add a node, what happens is you need to add entire column and entire row in this data structure. And if you want to store your matrix in some compact form, so essentially you're creating a copy. So its cost is V square. But the cost of finding adjacent V is basically traversing a row or a column of this matrix. So this is order n. This ends the introduction of graph. Now we will look at algorithms over graphs and see which problems can be solved using graphs in